um, you remember we're talking about the particle in a one-dimensional box, right? And with the calculations that we were doing on the whiteboard, we found a certain special class of solutions, right? The separable solutions. Uh, that is, we could separate them into a function of x times a function of time. So these are also known as the stationary solutions because the probability density is not changing in time. Or they're also known as um, the solutions with specific energy. Um, so here in the Mathematica notebook, um, I want to visualize what do these solutions look like, and then what do combinations of these solutions look like. Okay, so here I've got this beginning setup. All right, so defining the energies E, the time independent lowercase psi, the time dependent uppercase psi, and then a general wave function, which is the sum of some C coefficient times a time dependent solution, special solution number n. Okay. Um, so these C coefficients are important, right? They're like in a recipe where you say, how much of each ingredient do you want to have? Okay, and so here, let's do an example. Well, here's the example that I showed you yesterday is pure state number one. Okay, so in this example, we put in just state number one. Okay, so C1 is one, the other C's are zero. Okay, and what that looks like is a wave function like this. Okay, so here you can see the real and imaginary parts that are going up and down. Right? But the wave function is not moving anywhere in x because it's a stationary solution. Right? And so then we worked out things like the probability density. It looks like this. It's concentrated right in the middle. Okay? Then we worked out the averages. That's what I calculated for you yesterday. Okay, now what about pure state number two? All right, well, so here, let's do it. Okay, so in this example, I put in that C2 is one, but the other C's are all zero. So that makes this thing pure state number two. Okay, what does this look like in time? All right, well, here in this picture, you can see the real and imaginary parts going up and down. All right, and once again, it looks like everything is just going up and down in place. Nothing is moving in X because, again, this is a stationary solution. Um, you can see that there's a node right in the middle, okay? And so the waves are going up and down more in this state than they were in the last state. And that goes along with this state having more energy than the last state, okay? The energy is all kinetic energy because there's no potential energy here, right? It's just kinetic energy. Kinetic energy is associated with derivatives of the wave function. So here, where there's an extra node, there are bigger derivatives of the wave function with respect to x. So more kinetic energy. That's what makes this a higher energy solution than the last one. All right. So this is the complex wave function as a function of position and time, right? And you remember the blue is the real part and orange is the imaginary part. Okay. Now we can take the absolute value squared of that. Okay. Here is a plot of the absolute value squared. That's the probability density. Okay. This is, well, it's not a movie, but I could have made a very boring movie out of this because it's not going anywhere because it's stationary. Okay. So we have this fixed probability density. And the probability density now has a node right in the middle, right? There's a place right in the middle where the probability is 0. So the probability is concentrated around 1/4 and around 3/4. All right. Now we can once again calculate averages of everything. Okay? So for example, we can calculate the average of x by taking psi star times x times psi and integrating that for x goes from 0 to a. Remember, a is equal to 1 in this numerical example. So we get out 1/2, right? The average x is 1/2, right? That's even though there is 0 probability of the particle being exactly at x equals 1/2, right? There's no probability there, but still that's the average because half the probability is less than half and half the probability is more than half. We can calculate the average of x squared and hence the standard deviation of x. Right? That is how much uncertainty there is in the x. Okay, so you see in this example, the standard deviation is 0.266, right? In the previous example, the standard deviation of x was 0.181, right? And so now there's a bigger standard deviation, which makes sense looking at the plot, right? Because the distribution is more spread out. It's less concentrated close to the average. Okay, how about the momentum? Okay. Well, get the average momentum by doing this integral sandwich, right? Psi star, then negative I h bar d by dx, then psi, right? Put that inside the integral, and we integrate, and we get 0, okay? Again, it's 0 average momentum because the average position is not changing, okay? And so the average momentum is related to the time derivative of the average position. Okay? We can get out the average momentum squared here, and then the standard deviation of the momentum, meaning the uncertainty of the momentum. And then we can get the product, the uncertainty in position times the uncertainty in momentum. Okay? And that product comes out to be the 1.67, again, in units where h bar is equal to 1, right? So it's 1.67 times h bar. Okay? So the uncertainty principle says that this has to be greater than or equal to 1/2 h bar. And so here, yeah, it's way greater than that, right? And so we're not at the limit imposed by the uncertainty principle. We're well above that limit. Okay. Questions so far about this kind of a state? All right. Does this all make sense to you, or is this just blowing you away? Or is this just totally obvious? I can't tell. You're too quiet. Okay. Well, what do you suppose would be happen with state number 3? Okay, so if you know what state number 1 looks like and what state number 2 looks like, what do you suppose state number 3 looks like? Let's figure that one out. Okay, let's see. Oh, whoops, there's something in the chat. Ooh, there's a comment in the chat. There will be 3 nodes. Yes, there will be an extra node compared to the last one. Right, good point. Okay, so if we do state number 3, we can see here it is at t equals 0. Here it, whoops, I have to execute this stuff. Ha ha ha, that's my mistake. Let's execute it. Okay, here is the movie. Here's the movie. Okay, so in the movie, you can see everything is going up and down. Again, it's just going up and down in place. It's not moving. And yes, there is an extra node. Now, for counting the nodes, I think most people would count this as 2 nodes, right? So the state number 1 has 0 nodes, state number 2 has 1 node, state number 3 has 2 nodes, right? But each, as you go to each additional state, you get 1 extra node. And so there's more and more x derivatives of the wave function. So more and more kinetic energy. All right, so this is the behavior of the wave function. We can again get the probability density, and again, it is stationary. This is another stationary state. So it's a stationary state with peaks here, right? And so peaks at x is, I guess, 1/6 and 1/2 and 5/6 or something like that. And again, we can calculate all these expectation values, right? So the average x is still 1/2. The average x is still right in the middle, right? But the uncertainty in x is getting even bigger. Do I calculate it? No, I didn't put it in. But anyway, the uncertainty in x is getting even bigger, right? This is, again, consistent with the uncertainty principle. It's way past the uncertainty principle limit now. One thing that I do calculate here is the average energy, the average of the Hamiltonian, and the average of the Hamiltonian squared, and then the uncertainty in energy. Once again, the uncertainty in the energy is 0, which it has to be because this is a state with a definite energy. That's a special property of these separable states. Okay, so now you've got the feeling about what any of these special solutions looks like. But, you know, the general solution doesn't have to be one of these special separable solutions. The general solution could well be a mixture of these solutions. So let's look at a mixture. Okay, so here I'll make a mixture of pure states, number 1 and number 2. Okay, and I'll do that by choosing the C coefficients. Okay, so I'll choose C1 is 1 over root 2, and C2 is 1 over root 2, and C3 is 0. So there's none of state 3. Okay, so the ingredients are sum of state 1 and sum of state 2. Later on, I'll talk about the interpretation of the C coefficients and why I would say 1 over root 2 and 1 over root 2. Okay, so now what? We can here make a plot of what that looks like at t equals 0. I'm supposed to execute this. Okay. And then here is a movie to show what that looks like as a function of time. You can see that this movie looks kind of different from the other ones that we had, because now it looks like stuff is moving from side to side, right? Sometimes there's more on one side, sometimes there's more on the other side. Okay, so let's figure out the probability density that goes with this. Okay, so our wave function has this form, right? So our wave function has a sine of pi x times 1 complex exponential plus a sine of 2 pi x times another complex exponential. Right? When we take the complex conjugate, that means we change the sign of I. We change minus I to plus I in both of those complex exponentials. Okay. So the probability density is multiplying out psi star times psi. In this case, it's a little bit tricky to do that multiplication. So luckily I made the computer do it, okay? And so here's the answer. And what did I do? Here, it comes out real. Oh, good, it better come out real. It's a probability. Probabilities better be real, okay? They better be positive or 0 and real. And now it has a time factor that when we multiply out all those complex exponentials, we get a time factor, this cosine of something times time, right? Is this thing normalized? Yes, it is, okay? So I'm checking it, that the normalization, the probability integrates to 1. Good, it better, okay? What does the movie of the probability density look like? Okay, well now the movie is, well, I was going to say not boring, but I'll just say the movie is less boring than the previous one. The movie now has some time dependence in it, right? The movie shows the probability moving back and forth from one side to the other side, okay? So this is like a quantum mechanical game of Pong, right? You guys know Pong? Any of you? Okay. That's like from when I was a kid. That was really high tech when I was a kid. All right. So this is like Pong, right? Because, the particle bounces back and forth inside the box from one side to the other. Okay. So that means that if we calculate the average x, I bet it's going to depend on time, right? It looks like it's going to depend on time. Okay. So we can calculate it, okay? So I'll tell the computer to calculate psi star times x times psi and integrate that for x goes from 0 to a. And yeah, sure enough, it has this dependence on time. It depends on the cosine of something times time. Okay? Or if I plot the average x, it's going back and forth, right? That's a plot of what you see in the movie. The average is going back and forth from side to side. Likewise, we can calculate the average momentum. Okay? So the average momentum is this integral of psi star times negative IH bar d by dx of psi. Right? That average momentum also depends on time. And you can see that the average momentum is the derivative of the average position multiplied by the mass, which is 1. Okay? And so that's the way it should be, right? That the average momentum shows how the average position is changing in time. Okay? So here is a plot of the average momentum for this mixture of states. Okay, I can also get out things like the average of x squared and the uncertainty in x. Now it's a little bit messy. It has some time dependence. Can also get out the average of p squared, so the uncertainty in p, which also has some time dependence. So the product of the uncertainty in x times the uncertainty in p, this is a real mess. It's got complicated time dependence. But does it satisfy the uncertainty principle? Well, let's make a plot of it and find out. Okay, so here's a plot of that product. Okay, so you can see it is changing in time, but it's always at least as big as about 0.69 times h bar. So it's bigger than a half h bar at all times. And so good, that satisfies the uncertainty principle. How about the average energy? Okay, the average energy is what we get by doing this calculation, okay? So it is psi star times the Hamiltonian operator times psi, integrated it over the whole thing. So it comes out to be 5/4 times pi squared, okay? Now, I wonder if this is, or how this number compares with the energy of state 1 or the energy of state 2. Okay, well, the energy of state 1, let's go back and find it. That was a half pi squared. Okay. What about the energy of state 2? That was 2 pi squared. Okay, so now I have a mixture of state 1 and state 2, and I get this average energy, which is 1.25 times pi squared. So it's just halfway in between the energy of state 1 and the energy of state 2. Well, that sort of makes sense, doesn't it? If you have a mixture of state 1 and state 2, then the energy is in between the energy of state 1 and state 2. And I can get the average of h squared, the Hamiltonian squared. So I can get the uncertainty in the total energy. And look, now the uncertainty in the total energy is not zero. Okay, that's unlike the pure states that we did before. Right? So this is not a pure state. This is a mixture. Okay? And because it's a mixture, it has uncertainty in the energy. Okay. For comparison, let's do a mixture of state 1 and state 3. So for that one, let's see. So here I put in C1 is 1 over root 2. C2 is 0. There's another state 2. Okay. C3 is 1 over root 2. Right. The movie of the wave function looks like this. Okay. So it's getting more complicated, but sometimes there's more right in the middle, and sometimes there's more out on the sides. Okay. And so if you look at the probability density, you can see it's sloshing back and forth between the middle and the sides, okay, for this mixture of state 1 and state 2. Okay. I also calculate all these averages again. Let me skip over that to save time. Okay. What about a mixture of states 1 and 2 and 3? Okay. So I'll make a mixture where C1 is 1 over root 3, and C2 is 1 over root 3, and C3 is 1 over root 3. Okay. Let's see what that looks like. Okay. So here's the wave function, okay? This is starting to be kind of a mess to look at, right? It's really going all over the place, okay? And for the probability density, here's a movie of the probability density. It's getting kind of messy now, but you can see sometimes it's really concentrated in one place, and then it gets spread around. And then sometimes it's really concentrated in another place, then it gets spread around again. But it is periodic in time, right? And so you do sometimes see the concentration one place and sometimes in another place. So it does go back and forth, okay? And so here's a plot of the average X, and here's a plot of the average P. And the average P is the derivative of the average X times the mass. Okay, so those are a few examples to keep in your mind, right? So when you see equations about what a wave function is mathematically, that's kind of abstract. And so it's nice to have specific things to imagine. So those are some things you can imagine. All right, now I want to go back to the whiteboard. Any Mathematica questions before I shut this off? No? Okay. Let me shut this off and then I'll reconnect the iPad.
Professor, I got one question.
Please, go ahead.
You talked a little bit about yesterday too, definite energy. What does it actually mean? I mean,
say the question again. I didn't understand.
What does definite energy actually mean?
Well, it means there's no uncertainty in the energy. Okay, so there is a single exact energy, okay, right? That's the definite energy, right? And so we've seen that we can calculate the uncertainty in anything, right, by taking the average of anything squared, right, minus the average of the anything quantity squared. Okay. So yeah, we can get the uncertainty of anything. And we see that, there's this uncertainty principle that has to do with the uncertainty in position and the uncertainty in momentum. Okay. But energy is another thing that might have a single definite value, or it might have some uncertainty. Okay? And so now I've shown you examples where there's a single definite energy. That's with any one of these pure states, a pure separable state. Right? Or we have examples with mixtures, and those things don't have a single definite energy, right? Those things have some uncertainty in the energy. Okay, so that's what I was trying to get at there. Okay, great points. Okay, so to connect up the iPad here, iPad cable, go. Okay, good. So what you could see in all of the examples that I've shown you is that the C coefficients are really important, right? The C coefficients determine, what pure state or mixture of states do you have, okay? So let's think about that, about the interpretation of the CN coefficients. Okay, so in my notes here, whoops, sorry, gotta get my notes out. In my notes here, right, you can say we have a state which is a combination of pure states. Okay, so we have a psi, the general psi of x and t is a sum over this integer n from 1 up to infinity, perhaps, of Cn times the position in, the position dependent, time independent pure state, this square root of 2 over a sine n pi x over a times the exponential of minus I ENT over h bar. Okay, so we want to know about these guys, right? What does it mean to have some amount of each of the pure states? Okay, so let's first check the normalization. I did that in Mathematica for my examples, but now let's do it in general, with this algebraic notation. Okay, so I want to know what is the integral from minus infinity to infinity of psi star of x and t times psi of x and t dx. Okay. And I want this to be 1 for all time. So let's do this integral. Okay. Well, first of all, we know that psi, well, I should have said psi is this thing for x between 0 and a. And it is 0 outside that range. Outside the box. Okay. So I only need to do this integral for x that goes from 0 to a, right? Everywhere else, the thing that's getting integrated is 0, okay? So I'll change the limits of integration to be 0 to a, like that. Okay, so now we have to plug this expression for psi into that integral and do the integral. Okay, let's do it. So this is an integral from 0 to a. Now I have psi star, okay? That's the complex conjugate of this psi. So it's the sum from n equals 1 to infinity, Cn, oh, I better say a conjugate because Cn might be a complex number, okay? So I'll put a star on it. Okay? Then square root of 2 over a, that's real. Okay, I don't have to put a star on that. Okay, then sine n pi x over a, that's real. I don't need a star on that. Then an exponential of plus I from the complex conjugate, e n t over h bar. Okay, this is all psi star. Okay, now I have to write down psi. Okay, so that's going to be a sum. Now, I was about to write down from n equals 1 to infinity, but you know, it's not good to use the same letter for different things in the same equation, right? So I already have the first term that's getting summed over n equals 1 to infinity. When I write it down again, I better not use the same letter again because there'd be a big risk of making a mistake and thinking that one n is the same as the other n when it doesn't have to be. Right? So I better use a different letter. How about L? Okay, L equals 1 to infinity. Okay, so this is how I write a script letter L. Okay, and so I'm doing script so that I won't get it confused with the number 1. Okay, so now I'll copy out what is psi. It's the sum from L equals 1 to infinity. Whoops, wrong pen. CL square root of 2 over a sine L pi x over a e to the minus I e L t over h bar. Okay, so this thing is just another copy of this psi, but I changed the summation index n to L. Okay, and it doesn't matter what I call the summation index because I have a loop over it. And in software, if you have a loop over some index, it doesn't matter what you call the index, it just matters what you do with it. Okay, so I have this product of sums, and I integrate that dx. Okay, how do we do this integral? All right, well, we have sums of over n, a sum over n, and a sum over L. Okay? But we can exchange the order of doing the summation and doing the integration. Okay, so let's do that. Okay, so I want to factor out everything that doesn't depend on x. Okay, so I have a sum where n equals 1 to infinity and a sum for L equals 1 to infinity. Okay, now let's factor out all the stuff that doesn't depend on X. Okay, so there's a Cn star and a Cl. Okay. There is a factor of root 2 over a and another factor of root 2 over a. So I can factor them out of the integral. Actually, I can even factor them out of the sum. I'll put it way over there, 2 over a. Okay, then I have these signs. They depend on X. I'll do them later. Okay. Then I have these exponential factors. Okay. So e to the plus I, e n t over h bar, and e to the minus I, e l t over h bar. Okay, and now I have the position dependent stuff. So an integral from 0 to a sine n pi x over a sine L pi x over a dx. Okay, now I want to just do this integral. Okay. So this is a definite integral which depends on the integers n and l. You know, how do we do this integral? Okay. This may be something that you have studied in your math classes, or maybe not. Somebody tell me, has anybody studied this kind of integral in math classes? Perhaps classes about Fourier series, right? It's the sort of thing that you might learn about when you're learning about Fourier series, okay? And so what I can try to remind you, right, is if you have the product, well, if you have any sine function, right, that's getting plotted from 0, x equals 0 to x equals a, it goes up and down some number of times. So this is one kind of a function, or maybe it goes up and down more times. Like that, right? Or maybe it goes up and down some other number of times. Like that, okay? These are not the world's greatest plots, but they'll do the job, okay? So these are examples for different values of the integer multiplying x in the sign. So what happens if L is not equal to n? Okay. If L is not equal to n, so if you have two different color plots in here, okay, like if you're multiplying the black one times the red one, then you get a product which is positive half the time and negative half the time. So it averages out to 0. Whoops. Then the integral equals 0. On the other hand, if L is equal to n, then the integral is, well, it's an integral of sine squared of L pi x over A dx. Okay. And the average value of the sine squared is a half. So we get A over 2. So the point is that this integral down here is either 0 or A over 2, depending on whether L and N are the same integer or different integers. Is this familiar to you from some math classes, or am I just making this up? Okay, this is familiar to you maybe, okay. So if we combine those two cases, we would say in both cases, we could write it as the integral equals A over 2 times delta ln, where this delta symbol is the Kronecker delta. And what it means is that delta ln equals 1 if L equals n, and 0 if L is not equal to n. Okay. Is this symbol familiar from math classes? I'm not seeing resounding confidence in that. Some yes, some no. Well, maybe. Okay. This is this kind of thing we're going to use a lot in quantum. Okay. So, so let's put that integral now into our expression down here. Okay. So let me copy and paste this. Oh, whoops, wrong thing. Lasso. Copy. Oops, what did I do? Let's try that again. Yeah, gotta learn how to do this thing. Copy. Paste. Well, that sort of worked. Push it off the screen. Stuff I don't like. Okay. So here, this is the normalization. Is equal to all this stuff. Okay. And here we have calculated that this thing is A over 2 delta ln. Very conveniently, this A over 2 cancels the 2 over A that it's in front of the equation. Okay. All right, now what? Now let's do the sum over L. Okay. So we want to do the sum over L. So that means we have here, we still have a sum over n. Okay, but what's left? We're summing over all the possible values of L from 1 to infinity, okay? But there's only one value of L which gives something non-zero here. That's when L is equal to n, right? All the values of L that are different from n give 0 right there. So forget about them, okay? We only want the value of L that's equal to n. Okay? So In this sum, we have Cn star times CL, but L is equal to N. So Cn. And then there's this exponential plus I ENT over H bar. And then we have an exponential of minus I EL, but L is equal to N. So En T over H bar. Now look, these exponential factors cancel each other. So we have just the sum of n equals 1 to infinity of Cn star Cn. Okay? Or equivalently, the sum of the magnitude of Cn squared. So we want this normalization to be equal to 1. Okay, so this tells us that the Cn magnitude squareds have to add up to 1. Okay, now you can see that is why I said my examples. For example, C1 is 1 over root 2 and C2 is 1 over root 2, right? Because if you square those things and add them up, you get 1, okay? Or I said C1 and C2 and C3 are each 1 over root 3, because if I square those things and add them up, I get 1. Okay, so I knew that in advance, and that's why I made those guesses. Okay, okay, so that's how, it wasn't just an accident that the wave function came out normalized, but I kind of knew the answer in advance. Now, that's part of the interpretation of the C's, that the magnitude squared of the C's has to add up to 1. Okay, now we can get a little bit more interpretation if we think about the expectation value of the Hamiltonian. So suppose we want to know the expectation value of the energy. Okay, so that's this expectation of the Hamiltonian. So it is going to be the integral of psi star of x and t times the Hamiltonian acting on psi of x and t integrated dx. Okay, now let's write these things out as sums. So that is the integral of, oh, now I've got to do this sum again. All right, the sum of n equals 1 to infinity Cn star square root blah, 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 2 over a sine n pi x over a e to the plus I E n t over h bar. Okay, then there's a Hamiltonian acting on the same thing, but written with the L's. So CL 2 over A sine L pi x over A e to the minus I E L t over h bar. Integrated dx. Okay, now here comes the real point of this calculation. Okay, the point of this calculation, I'm not going to keep rewriting the same thing because it's too much work to keep rewriting. Okay, so instead, let's just take the Hamiltonian operator. You know, this is a second derivative with respect to x. So let's let it do its operation. So we'll let it operate there on this sign of L pi x over A. Okay. What does it do? Okay, well, we already know what the Hamiltonian does to a pure state. What H does to a pure state, a separable state, a definite energy state, is that H acting on that state, psi L, gives EL psi L. That's the time independent Schrodinger equation, which we were solving right from the beginning. Okay. So that means now we have our integral of, this first set of things, sum of n equals 1 to infinity, Cn star. And pi x over A, e to the, I'm not going to keep doing this for the rest of my life. I'm just going to do it a few more times and then I'll make a shorter notation. Okay, so we have a sum of L equals 1 to infinity, CL root 2 over A. And so now it is an EL sine L pi x over A, e to the minus I EL t over h bar dx. So now this calculation is just like the last one that I did, except that there's an extra factor of EL there, which there wasn't before. Okay, so now I'll say just, let's repeat the same procedure. And I'm going to skip ahead to the answer. Okay, the answer is that the average H is now a sum over all these n's of Cn star Cn times En. Okay, so there was an EL down here, but I hit it with the Kronecker delta, and so the L turns into an N. Okay, so it looks just like this. Okay, so it's the same as the result from the last time, except for this factor of En, which wasn't there before. So this is the sum of n equals 1 to infinity of Cn magnitude squared times En. So this tells us even more about the interpretation of the C coefficients. Okay? It tells us that Cn squared is a probability. It is a probability that, how can I say it? If you observe the system you measure the energy En, right? Or in other words, the probability that if you observe the system, you see it is in state N, okay? So if I make up a mixture of states, like for example, the first thing that I did, right, where C1 and C2 are each 1/√2, okay? This system is in a mixture of states 1 and 2, okay? But if I observe it and I say, I'll look at it, at one moment, and am I going to find state 1 or am I going to find state 2? And there's going to be a 50-50 probability, a half-half probability, okay? Because the 1/√2 squared is a half, okay? And so with 1/2 probability, if I observe it, I'll say, oh, this is in state 1 with energy E1. Or with a half probability, if I observe it, I'll say, oh, this is in state 2 with energy E2. So on average, the average energy, which is this thing, the energy will come out halfway between the energy of state 1 and state 2, which is what I showed you in the Mathematica example. Okay, that the energy came out halfway between the energy of the two things, right? Whereas, I could have made an example where, C1 is the square root of 0.9 and C2 is the square root of 0.1. Right? If I add up those things squared, I also get 1. So that's normalized, okay? And this example would be pretty close to state number 1 with just a little bit of state number 2, okay? And so this example would have an average energy that's pretty close to the energy of state 1, okay? And just a little bit towards the energy of state 2. Okay? So there'd be a 90% chance, if I make an observation, there'd be a 90% chance I'd say, oh, this is in state 1 with energy E1, and only a 10% chance that I would say, oh, this is in state 2 with energy E2. Okay, so this is the beginning of thinking about quantum states, right? That here we have 2 quantum states, state 1 and state 2, and there can be mixtures of them. And so the particle can be in some mixture of state 1 and state 2, or state 3, or state 300, any positive integer. All right, so this is telling you something about the interpretation of the C coefficients. And now that you see that the C coefficients are important, you might be wondering, what determines the C coefficients? In the examples so far, I just made them up. Ha, ha, ha. I get to do that because I'm teaching here. But what if you don't get to just make them up, right? What if you have a problem that you want to solve and you want to know in some problem what determines the C coefficients, right? And the answer is the initial conditions. That is the vital bit of information that we haven't used yet. Okay, so far we've used two kinds of information for solving this problem. Okay, we have used Schrodinger's equation, that is the differential equation, and we used the boundary conditions. But in any math problem, partial differential equation problem, solving a partial differential equation, you have to use three kinds of information, right? The differential equation and the boundary conditions and the initial conditions, right? So we've used 2 out of 3 so far, but we need to use the initial conditions also to determine what are the C coefficients. Okay. So how do we do that? Okay. Well, there's a simple way if you are very lucky, and then there's a general way. Okay. So let's first say the simple things. Okay. So if you are very lucky, okay, if you are very lucky, then your initial condition matches one of the pure states. The pure states, well, or I could say one of the separable solutions, or one of the stationary solutions, whatever you call them, right? So if you are very lucky, then your initial condition, that is psi initial as a function of x, right? Or in other words, psi of x and 0. Okay, so that's what happens at time equals 0. Okay, if you are very lucky, this is equal to one of the pure states. So for example, we could say it's equal to psi 13 of x, okay? And so that means it's equal to the square root of 2 over a sine 13 pi x over a. Okay, so in this case, if I'm doing a homework problem and this is the initial condition, I say, oh boy, 13 is my lucky number here, right? I say, look, this is one of the separable states. So I know how separable state 13 evolves in time. I know that it evolves in time as psi of x and t is this position dependent part, this position dependent part, the 2 over a sine 13 pi x over a times the exponential e to the minus I e 13 t over h bar. Okay, so I'm done, right? This is then the answer of what happens here. Or in other words, C13 is equal to 1 and C1 is 0, C2 is 0, C12 is 0, right, etc. Right? All the other guys are 0. Okay, and this is a solution because it satisfies everything. It satisfies Schrodinger's equation, check. It satisfies the boundary conditions, check, right? Those things automatically work because we've designed everything so that they work, okay? And it satisfies the initial condition because if I plug in t equals 0 right there, then this is the exponential of 0, so it's 1. And so psi is just the thing that we were looking for. Okay, so this is how it works if you are very lucky. Okay. If you are medium lucky, okay, then the initial condition is the sum of a few pure states. So it might be that the initial condition, so psi initial as a function of x, right? Or psi of x and 0 is, 1 over root 2 times state 13. So that's 2 over a sine 13 pi x over a plus 1 over root 2 times state 14. Okay, so sine 14 pi x over a. Okay, so then you would look at that and say, oh, I recognize that, right? That's just the sum of two of the pure states that I know about. Okay. Then that means C13 is 1 over root 2, and C14 is 1 over root 2. And all the other C's are 0. Okay. So then you know how this kind of thing evolves in time. This is just, a special case of the general solution we have with two terms there. So we get out psi of x and t is going to be 1 over root 2 times 13 e to the minus I e 13 t over h bar plus 1 over root 2 psi 14 of x e to the minus I e 14 t over h bar. Okay, and then you're done, right? So this is just like the mixed problems, the mixed examples that I showed you in the last Mathematica file. Okay, so this is all right. It's not too bad if you're medium lucky. Okay, what if you are unlucky? What if you are unlucky? Then the initial condition is something completely different. So For example, maybe somebody will tell you that the initial condition of X or psi of X0 is 1 minus X squared, a parabola like that. X squared divided by a over 2 squared, something like that, right? Times a normalization factor. Okay. And now you say a parabola? That's not on my list of solutions. What am I going to do with a parabola? That is what I'm going to show you on Thursday. Okay, so I'm out of time now. So on Thursday, I'll show you what to do in the unlucky case that the initial wave function is something completely different from one of the choices on the menu. Okay, so let's hold off and I'll get to that on Thursday and I'll have some nice mathematical example for that one too. Remember, you've got a homework assignment due on Thursday, so please email that to me if you have not done so already. Okay, I will see you then. Of course, I'll stick around and answer questions now.